so these questions, ethane 1,2-diamine is a useful reagent in organic chemistry. Okay, so diamine, so how does it look like? 2 carbon because of ethane. Diamine means you have NH2 on both sides. The rest are just normal H, 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 and H. Okay, this is ethane diamine. So part 1, explain how the amino group means the NH2. Okay, the NH2 is amino group. In ethane 1,2-diamine, allow the molecule to act as a Bronsted-Lowry base. Bronsted-Lowry base is proton acceptor. So why? Because it has lone pair. So it has lone pair, then it can act as proton acceptor or lone pair acceptor. Sorry, it is H plus proton acceptor. H plus acceptor. So we just say that N has lone pair. So N receives H plus. Okay, so part 2, write an equation for the reactions of ethane 1,2-diamine with an excess of hydrochloric acid. So hydrochloric acid will neutralize the basic amino group. So we write down the equation in this way. We put it as structural formula. H2NCH2CH2 NH2 plus HCl. So I need 2 HCl. One is to neutralize the amino group on the left. Another one is to neutralize the amino group on the right. So that will form ClH3N, CH2, CH2, NH3Cl. Okay, so that forms this product. Now let us see the next questions. So the first question just now is still simple. Okay, now this is the other questions. Seems like more complicated. Nitrobenzene C6H5NO2 can be reduced to phenylamine C6H5NH2 in acid solutions in a 2-steps process. So if you still remember this, if you want to change nitrobenzene to phenylamine, so we have to put HCl plus tin. Okay, so number 1, balance the half equation for these reactions to work out how many moles of electrons are needed to reduce 1 mole of nitrobenzene. Okay, so they want us to balance the equation. Okay, so we are changing nitrobenzene to phenylamine. Okay, now first let's say we balance the oxygen first. As you can see, NO2, there are 2 oxygen. So here the oxygen come from H2O. So we balance the oxygen here by having 2 here. So oxygen is balanced when you put 2 to the H2O. Now let's balance the hydrogen then. Hydrogens. So we have H2 as the extra hydrogen. And then here another 4 hydrogen as the extra hydrogens compared to left hand side. So we need 4H. We need 2 plus 4. We need 6H plus to balance the hydrogens. 6 here. Okay. Now we have to balance the charge. As you can see, right hand side they are all neutral, no charge. So left hand side I have 6H plus that is positively charged. So I need 6 electrons to balance the charge. Okay. The reducing agent normally used is granulated tin. So as I see here, as I mentioned, we need tin and HCl, right? And concentrated hydrochloric acid. In the first step, the reductions of nitrobenzene to phenyl ammonium chloride can be represented by the equation shown. Use oxidation number or electrons transferred to balance these equations. You might find your answer to part 1 useful. Okay, so this is our equation in part 1. Okay, now they want us to find out the equation here. Okay, so balance the equation. Now, they already give you hints. They say you have to use this to help. So how? Let's look at, basically this is where it involves 6 electrons here. 6 electrons. So let's see who is donating electron. So as you can see easily, Sn to Sn4 plus here. So I write down the oxidation number. This is 0. This is positive 4. So this is the one that donate electron. This is oxidize. So Sn become Sn4 plus 4 electrons. Okay. So our equation here, A part 1, involve 6 electrons. Our second equation here, 4 electrons. So to find the overall equation, the main idea is we have to make the electrons the same. So the common multiple of 6 and 4 is 12. Okay, 12. So we times 2 to change this to 12 electrons. So we times 2. So it becomes 2. This becomes 12. This becomes 12. This becomes 2. This becomes 4. Okay, so I put in green color. So I times 3 for the tin equation here to change everything to 12. To change the electron to 12 electron. So I times 3. Yeah? So 3, and 12 electrons then. So once you have these two equations with the same number of electrons, then it helps us. It helps us to find the overall equation. Okay, so first of all, let's look at C6H5NO2. Okay, so we put 2 for this. So why 2? Because here you see, here 2, 2 of it. So I bring it down. HCl 12. Okay, 12. So maybe I put later because even this that involves some hydrogen also. This one then need HCl. This one involves some hydrogen. I put this later. Okay, I look at tin first. Tin I put 3 because of this part. Okay, I put 3. The Sn4 plus has to be 3 as well. So here I put 3. And then the C6H5 and H2. C6H5 and H2, which is this one, we already decide is 2. So we put here 2. H2O, I get 4. Okay, so I put here 4. So the only thing that I need to balance is the HCl. So we can balance this easily by looking at the chloride. So you have 2 chloride from here, and then 3 times 4 is 12 chloride. So we have 14 chloride. So we put 14 there. So 14 HCl. Okay, so that is how we balance the equation. Now we look at part B. When 5.0 gram of nitrobenzene was reduced in these reactions. 4.2 gram of phenyl ammonium chloride, C6H5NH3Cl, was produced. Okay, so that means this is the C6H5NO2, which is nitrobenzene. You use 5 gram. Okay, you use 5 gram. And then phenyl ammonium chloride is this one. This one produced 4.2 gram. So I write down first. This is 5 gram. This is 4.2 gram. So they ask you to calculate the percentage yield. Percentage yield. What is percentage yield? I write the formula. Okay, so this is the formula. Percentage yield is actual yield times 100 divided by theoretical yield. Theoretical yield is the one that we get it from the chemical equation. Actual yield is the one that you get it from practical. So the thing is, should we use gram? Should we use gram for the actual yield and theoretical yield, or should we use mass? Should we use gram or should we use mole? That is the thing. Okay, so what am I going to say is both will be fine. Both will be fine. So it's up to you. You want to use mass or you want to use gram? It's up to you. Gram or mole. It's up to you. So let's say I use mole. So if I use mole, right, I'm going to change the 5 gram to mole, and I'm going to change the 4.2 to mole as well. Okay, so mole of nitrobenzene, C6H5NO2. 5 divided by molar mass, 1, 2, 3. Okay, so that is 5 over 1, 2, 3. I just leave it like that first. And then by right, if we follow equation, we are talking about theoretical yield now. If we follow equation, this is 2 mole, this is also 2 mole. So if this one is 5 over 1, 2, 3 mole, then the product should be 5 over 1, 2, 3 mole also. That is the theory based on chemical equation. So I write down first. This is supposed to be the mole of C6H5NH3Cl also. The mole should be the same one. But in practical, we don't get that mole. We get 4.2 over the molar mass. We get lesser in fact, if you go and count the mole. Okay, so now how are we going to put it in equation? 4.2 over 4.2 is the actual yield. So I change it to mole. I divide by the molar mass. This is the actual yield in mole. The theoretical yield in mole is the mole of the product, C6H5NH3Cl. So which is 5 over 1, 2, 3. Then I times 100%. Then I get 79.8%. So this is the percentage yield, 79.8%. Okay, part C. Following the reaction in B, an excess of NaOH was added to liberate phenylamine from phenylammonium chloride. So what happened is you take the phenylammonium chloride, which is this one, phenylammonium chloride. You react with NaOH, then they will form phenylamine. Okay, so now calculate the mass of phenylamine produced when 4.20 gram of phenylammonium chloride react with an excess of NaOH. Okay, so to do this, we need the equation first. C6H5NH3Cl react with NaOH. So it forms C6H5NH2 plus NaCl plus H2O. Okay, so they form this, and the equation is already balanced straight away. Let's find out the mole. This is 4.20 over 129.5. So according to the mole ratio, this will be the same, 4.20, 129.5. As you can see the equation, this is 1 mole to produce 1 mole. So they have the same mole ratio, so the mole should be equal. Okay, but they want the mass. So mass is where we take the mole of this one, we multiply with molar mass, which is 93, and then we get 3.02. That's the mass of phenylamines obtained. And now okay, this one, the final volume of the alkaline solution of phenylamine in part 1 was 25.0 cm3. The okay, that is the volume in alkaline solution, because you add NaOH to it, right? So that's why it's alkaline solution. So it's 25.0 cm3. The phenylamine was extracted by additions of 50 cm3 of dichloromethane. After the extraction, the dichloromethane layer contained 2.68 gram of phenylamine. Use the data to calculate the partition coefficient, K partition of phenylamine between dichloromethane and water. Okay, so what happened here is, I try to draw out. Initially, the phenylamine is in the aqueous solution. Okay, it is in the aqueous. Of course, now you add some organic solvent, which is dichloromethane. So that is the dichloromethane, okay, which is the something like oil, oil will float, and the alkaline solution is basically aqueous solution. So this is the alkaline solutions or aqueous solutions. Okay. And the solute here, these two are the solvent. Water is the solvent. Dichloromethane is organic solvent. The solute inside here is the phenylamine, so which dissolve here as well as there. Okay, so they dissolve in two parts. And of course, we haven't learned this chapter yet, so I just tell you straight away first. So what is K partition then? K partitions. Okay, K partition is where you have to find out the concentrations of the solute in the first solvent to the second solvent. So the first solvent is dichloromethane. So we do like this. K partition is phenylamine in dichloromethane. We use gram per cm cube over phenylamine in water. For this, it is again gram per cm cube. Okay. So we count this, then you get a number, and that number will be the answer. Okay, so why dichloromethane on top? Because we have to follow question. The question mentioned dichloromethane first, and then we put it on top, and water at the bottom. Okay, now we have to find the concentration in gram per cm cube. So the question said after the extraction. So initially we have 3.02 of phenylamine, where they're all in alkaline solution. Now you add some dichloromethane inside. So some go to the dichloromethane. So they say 2.68 gram go to the dichloromethane. So that means there are 2.68 gram of phenylamine over here, and at the bottom we have the minus 3.02 minus 2.68, so which is 0.336 gram of phenylamine remain in the aqueous solutions. So most of them go to the organic solvent already. So some remain in the aqueous solution. Okay, now we need to know the volume also. As you can see, this is the volume of the aqueous solution, 25 cm cube. Okay, so let's write down first, 25 cm cube, whereas 50 cm cube is the volume of the dichloromethane. So 50 cm cube. So let's write down this as well. 50 cm cube. Okay, so now we can count it. Just use mass divided by volume. So 2.68 divided by 50 over 0.336 divided by 25. Then we count it, we get 3.99. 3.99 is the K partition.